See what happens when the waves hit the barrier. It's very faint, but they're going through. Can you see? Propagating out. Okay. I am going to. Go away. I'm going to increase the slit width slightly. That'll let more light through. Watch the intensity measurement on the right. Okay. Something cool is happening there. Are you seeing the pattern you expected to see? There's a peak in the middle, and there's like a low bit, another peak, and a low bit, and a peak, and a low bit. Is that what you expected? It's like an interference pattern of some kind, right? It's interference. Okay. The light that's going around this part of it is interfering with the light going around that part of it. Okay, across the different parts of the slit. So we actually get interference with a single slit. Let's not think about that right now. Let's make it two slits. Closer together. Here we go. So we got a peak here, we got a peak right here. Little trough. You can kind of see the troughs really well, right? Okay. What's going to happen if I increase slit separation? Votes for the pattern is going to get closer together. Votes for the pattern is going to get farther apart. Votes for nothing's going to change. Votes for I'm terrified of raising my hand because I could be wrong. The first one? Let's move the slits farther apart and find out what happens.
Oh, that's not what
What's happened to the pattern? Right? Well, it's less intensity. What's happened to the pattern? It's gotten closer together, right? Everything's gotten bunched together. So it actually gets tighter as the slits get farther apart. When they're close together, the pattern gets lighter. Kind of moves yin and yang like that. That's weird. What will happen if I change to blue light? Tighter together? Votes for tighter together if I change to blue light. Randy, you kind of have to vote for your own.
Oh, I was assuming that was good.
Votes for farther apart if I go to blue light. Votes for no change at all. Going to blue light now, boss. Oh, what's that blue? Oh, there we go. That one's pretty pretty, isn't it? What's happened? It's tighter together. That one makes a lot of sense, I think, just intuitively, right? The wavelength is shorter. The tightness of that pattern has got to depend on the places where the waves go through two different slits meet at peak to peak, right? Well, the peak to peak depends on the wavelength, right? Some integer number of wavelengths in between them. As the wavelength gets smaller, you should be able to get those closer together, right? Because that's what's setting all this distance. What would happen if I go purple?
Can you get closer?
Tighter still. I like watching it spread out. Man, you're gonna be like that? With the slits a little bit clearer. A little more light through. You can see it on the graph. I can see it on the graph. You guys see it on the graph? Nope. I can just barely see the graph. You can see a few bumps. Yeah, and they're very close together. Okay. That seemed a little weird the way that happened. Okay. Not sure if you had that sort of effect at the very end. Okay. So light has this weird wave property. Okay. Each barrier acts like a little source. I mean, the light's always acting like, each wavefront is acting like a source, right? It's useful when you encounter a barrier, though, if you can see then what's going to happen as light leaves around that barrier, right? you can figure out the proper interference pattern. On Friday, we'll add the math behind this, okay? Although I just sketched out the rough idea. You're going to be interested in where the peaks are going to be peaks and where the peaks are going to be troughs. So you just have to look at the path length each one's going to take to figure out how far it took to get there, how many different cycles, right? How many wavelengths, okay? And that will tell you everything you need to know, okay? And I think it was about, yep, 20 times. So,